In this lecture, we'll be discussing about a second dimensionality reduction technique, what we call singular value decomposition. So just keep it in mind, this is another linear dimensionality reduction, just like principal component analysis. Okay. So just a little bit recall about the PCA steps. Given a data matrix dm times n, we have to actually first estimate a covariance matrix for this data matrix. So here the covariance matrix is A, n times n is the feature dimension. And then you need to solve this linear equation, okay? So that will give you the corresponding eigenvectors and eigenvalues, and you have to choose the eigenvectors with the maximum eigenvalues, depending on like how many components you want to select, okay? So in contrast, singular value decomposition, we have to follow some notational differences. So here A is your data matrix, okay, and it is transposed. That means here our data matrix D was recording data on a row-wise format. The columns were the features, just like in any tabular data. But here we transform the data, so your rows are actually your features and columns are your data items, okay? If we have A in this form, M is your number of features and N is the number of data points, okay? So what does singular value decomposition actually does? It directly works on your data matrix and decomposes into three matrices, U, S, and V, okay? So U is of size M times M. M is your number of features. And then this is called what we call singular matrix. So this is with the size M times N. And then you will have a big matrix if you have a big number of data points, what is called V, okay? So let's take an example and explain the scenario, so it will be much intuitive and clear. Here A is your data matrix and we recorded data in a column-wise format. So 3, 2 is our first, 2, 3 is our second, and then 2 minus 2 is our last data point, okay? So you have a 2 times 3 matrix. So your A would be of size 2 by 2, right? And then you have to solve this linear equation, so that will give you 2 eigenvalues and 2 eigenvectors, right? So this is a 2 by 2 matrix, if you recall what we did in our PCA presentation. So just keep it in mind that this will be A transpose A minus identity matrix times X. So you have to solve this equation, and then you will get 2 eigenvectors and their corresponding eigenvalues, okay? So the eigenvalues are 25 and 9. And so you have to solve another linear system, what is of the format A transpose A minus A and negative I and then X bar, okay? Here your data matrix is of size 3 by 3 because you have 3 data points, okay? So if you solve this, you will have 3 eigenvectors and 3 eigenvalues. But interestingly, if you pay attention, you see these eigenvalues are actually just like the same eigenvalue for the solution of A transpose minus I X, okay? So you have to solve this linear equation. You got 2 eigenvectors, 2 eigenvalues. You solve this linear equation. You got 3 eigenvalues, 3 eigenvectors. Because your data is 2 by 3 matrix, okay? And these eigenvalues for both the solutions are the same. What you have to do, you have to take the square root of these eigenvalues, okay? So if you take the square root of 25, 5, and then square root of 9 is 3, okay? So if you look at the solution now, so you will have the first 2 eigenvectors, and then you have a matrix with their square root of the corresponding eigenvalues of the first solution, and then you will have the 3 eigenvectors coming from this matrix, okay? So these values are not, we are calling anymore eigenvalues. These are, we are calling singular values because these are the square root of those eigenvalues, okay? So this will be your solution. And because your feature dimension is 2, so you will actually pick up the corresponding eigenvectors based on these eigenvalues. So this video description will include a notebook demonstrating a practical application, just like we have done for the PCA presentation. Thank you.